All right, here we are to finish chapter 8. And we're gonna, so the first section, we did hypothesis testing for the population mean that maybe a change happened because of, some drug study or something. And we looked at those to see if that change happened with, if we knew the population standard deviation. And then in 8.2, we looked at what if we didn't know the population standard deviation. We used the t-values for that. And now we're going to look at the probability of success, the proportion, and testing that and see if that has changed. And so it's going to be very similar to what we've already done. Again, the calculations are going to be a little bit different because we're talking about proportions and probabilities of successes, but the general idea is going to be the same as what we did in 8.1 and 8.2. All right, so we're still going to set up null hypothesis, alternative hypothesis. Again, the null hypothesis is going to include the default value, the equal to value, and then the alternative will be, what we're expecting as a change in that value. We're going to assume our samples are large enough. Again, the way we're going to check that is we're going to make that predicted value, predicted number of successes, the mean there should be more than 5, and then our predicted number of failures should also be more than 5, just like we did in the previous ones. And so that should be true in all these cases, in which case we're just going to use the z-values to do these calculations for these intervals, or to test these values. I should say intervals. We're not doing intervals. That was chapter 7. All right, so we're going to be given some information. We're going to be given the predicted value, and we're going to use this to craft the null hypothesis. We're going to be given, from that, we're going to calculate the predicted chance of failure. We're also going to be given information to calculate the sample proportion, or the predicted probability of success from the sample. And again, the way we calculate that is how many successes did we get in the sample, and out of how many trials did we take. And that ratio there, that proportion, is going to be our sample proportion. And then we're also going to be given a level of success of significance that we're going to use to calculate our z-value for this. All right. What we're going to do, we're going to write these hypothesis tests. We're going to use the idea whether it's going to be a one-tailed test or a two-tailed test. Again, the two-tailed test usually occurs when you say it's just different from the predicted value, the predicted probability of success. And the one-tailed test is when you're actually making a claim that it's bigger or it's smaller than the predicted, not just different in some way. We're going to find the sample test statistics, and we're going to use our formula very similar to what we did before. We're going to subtract our sample statistics from our population parameter, and then we're going to divide that by the standard error. And again, I'm going to manipulate this formula a little bit and just use this version of it. And again, that's pretty similar to what we did in 8.1 and 8.2. So, all right. Then we're going to calculate our p-value. And again, our p-value is the probability that if the population proportion was what we say it should be, we would land at that value or more extreme, that test value, that value or more extreme, more towards one of the edges, either the upper edge or the bottom edge. That's going to be our p-value. And again, because proportions are always between 0 and 1, all these numbers are going to be like decimal values. And so you're going to have to be careful with this, that you're doing the correct comparison of values. You're keeping straight what's what. Are we talking about a p-value, the probability you're at that spot or more extreme, or are we talking about the probability of success? So try to keep those things straight. It can be confusing if you're not careful. We're going to determine whether we should reject the null hypothesis or not. And again, the way we come to that conclusion is we look at this p-value and we compare it to that alpha value that we're given in the problem. And again, if we say the alpha value is 0.05, we have a 5% level of significance, then, if you get a p-value of 0.04, then you would reject it. And if you got a p-value of 0.06, you would not reject the null hypothesis. So that's going to be your cutoff. You're like, this is the amount of chance that I could be wrong, and I'm still willing to make, to reject the null hypothesis. All right, so let's look at page 476, number 9 here. 476, number 9. All right, is the natural crime rate really going down? Some sociologists say yes. They say that the reason for the decline in crime rates in 1980 and 1990s is demographics. It seems that the population is aging and older people commit fewer crimes. According to the FBI, the Justice Department, 70% of all arrests are males between 15 and 34. Suppose you're a sociologist in Rock Springs, Wyoming, and a random sample police file showed that 32 arrests, so last month, 24 were male, aged 15 to 34. Use a 1% level of significance to test the claim that the population proportion of such arrests in Springs is different from 70%. So they're saying 70% should fall in this age category. That's our predicted proportion. And then we got a sample size of 32. And within that, we found 24 were in that age category. And where you're going to use an alpha level of 0.01, 1%. Okay. So our null hypothesis is that our proportion is the same as this. And our alternative would be that it's not the same. This is a two-tailed test. So claim that the population of such is different. Notice it's not saying more than that or less than that. It's just saying it's different. And you might see why at this stage we might make that claim. I haven't actually calculated the sample statistic yet. So I don't even know if it's more or less than that yet. I need to calculate it before I can make that prediction. I'm just saying it might be different. The question is it different here than it is, nationwide? Is there a big difference there? So it's a two-tailed test. So now let's what's it say? What we're going to do first is we're going to figure out, whether we should be using this. So what's our predicted number of successes if the population proportion is true? 70% of crimes or arrests are made to people in the age category. And so if you multiply that by 32, we should get 22.4. That's predicted more than 5. And then if we figure out our failure, 9.6, that should be, again, more than 5. So this is a large enough sample. It's basically what we're saying here. It's also bigger than 30. So we didn't have to check that, but that's just a safe thing. All right, so let's calculate our proportion here. So we take our number of successes. Again, success doesn't mean good. It just means it's what we're looking at right now. So we had 24 individuals within that category out of 32. That gave us a probability of 0.75 within this area here. Where is this? Rock Spring, Wyoming. In these cases, 75% of those arrested in that area fall in this group here. All right, so let's calculate our z-value. So we're doing our z-value, z minus 0.75 minus 0.70. Divide that by our sample size of 32, and then, multiply it by the square root of our sample size, 32, and then divide by the product of our probability of success times our probability of failure. And that gave us a z-value of 0.62. So now if I go to my z table, hopefully I have that somewhere here. Let's look through my papers real fast, or otherwise I can just flip to the book and find it there. This looks like it. Okay, z-values. So notice this is positive. So let me get in here. I got a, oops, what happened here? All right, I got a z-value of that. So to go from 0.62 and more extreme would be go that way. But of course, my table isn't set up to do that. So what I'm going to do is I'm going to say, what's the probability that z, or I'm going to do 1 minus the probability that z is less than or equal to 0.62. And so 1 minus 0.62 is 0.7324. So let's subtract that. 1 minus 0.7324. And I got a value of 0.2676. That's the probability I would fall in that area. Now, this is not my p-value, though. My p-value, since this was a two-tailed test, is going to be this number times 2. Because the probability is, what would you get this value or that much at negative 0.62 the other way? That's what we're looking at. So I'm going to double that. That's going to give me 0.5432, or more than 53% chance I would hit that value in more extreme either way. And so clearly I'm not going to reject the null hypothesis. So it's nowhere near 1%. So within this city here that we're looking at, we're going to say, yeah, it looks like it's probably still around that nationwide average. This doesn't look like, this group is having a significant number higher level crime rate in that area. It looks like it matches the population at large. So with that two-tailed test, you're going to have to double that value, just like we did in 8.1. Okay. And so, nope, can't say it's different. Can't say it's different. It might be. Again, we just don't have any evidence to say it is. All right, so a few comments. The bigger your z-value is, the smaller your p-value is, right? So the farther your bigger your z-value is, the farther you are out to the edge. If this is like, let's say this is a little z and this is a big z-value, you can see how much space is out towards the edge. It's a lot smaller. So, and the same thing with the negative little z and a negative big z value. The smaller the edge is. So the larger z value, that means that you're farther away from what you would expect to get. All right. And that also means that the larger the z value is, the less likely that your null hypothesis is going to be true. Or alternatively, the smaller the z value is, the more likely you're not going to reject the null hypothesis, that the null hypothesis probably is still true, or at least you're not going to be able to say it's not. All right, so a few things that can affect the size, specifically increasing the size of the z. What could cause you to get farther to the edge? So one of the things that could do it is just a basic difference between your predicted value and your sample value. The bigger that difference is, the more likely you're pushed off to one of those side areas. So the more likely the null hypothesis isn't true. I mean, that should be pretty obvious. If I predict that there's a 20% chance of success and I do a sample and I get 45% chance of success, that's a lot more likely to prove that the null hypothesis, that predicted value isn't accurate, than if I got 22% chance of success and it was predicted to be 20. The farther I'm away from that predicted value, the bigger the z value is, and therefore the more likely I'm going to reject the null hypothesis. Another thing that could affect the size of it: larger sample sizes. So this might seem counterintuitive, but what's happening here is, if the sample size gets, let's say the difference between my sample and the predicted was, there was a 0.02 difference there between those two. Okay. But the significance of that difference is different based on the sample size. If I have a sample of 30 and I get that, or I have a sample of 30,000 and I get that, well, the bigger the sample size, the smaller this difference should get. The more closely my sample proportion should match the predicted proportion, if the predicted proportion is true. So even if this part is the same size, if my sample size gets bigger, that's actually going to push me farther away, because it's going to say, oh, you're not right next to you're not super close to the population proportion that we predicted, and you have a big sample, that means you're actually less likely to be correct. You know, the predicted value is less likely to be correct. So the larger the sample size, that's actually going to move you farther away. Even if this difference here stays the same, it's going to move you farther away. So that might seem counterintuitive, but it's accurate. It's accurate. Basically, the larger the sample size, the more likely this is the true number, or at least close to it. The bigger the sample size, okay? The more likely that your sample proportion is closer to the actual value, the bigger the sample size. So, and then the farther the probability, predicted probability proportion is from 0.5, and we saw that, remember when we did some comparisons, multiplying probability of failure, probability of success, we saw that the farther away from 0.5 you were, either way, that caused that product to be smaller, which in effect ends up making this Z value getting bigger because of that. So these are the three things that could affect that. Hint, hint, wink, wink. Put that in your notes somewhere because you're going to need it later on. All right. Okay, so let's, just like in A2, one thing we could do instead of calculating the Z values is we could calculate our predicted Z value for failure and then go by that using these critical values. Again, you'd use the alpha and determine whether it's a one tail or two test. If the Z value falls in that critical range, we could reject the null hypothesis. So this is just like kind of that alternative way we talked about in 8.2, how you could do it. This is an option to do it that way. If you want to do it that way, you don't have to. You can do it like how we started here. So let's see number 17 here, or sorry, yeah. So 24 asks us to see number 17. So let's go to 17. Report that 74% of the general consumer population in the United States is loyal to an automobile manufacturer of their choice. So let's see, P equals 0.74. Suppose Chevrolet did a study of random sample of 106 Chevrolet owners. So N equals 106, and found that 490 of them would buy another Chevrolet. Does this indicate that the population proportion of consumers loyal to Chevrolet is more than 47% or 0.46? Okay, and then use that alpha value of 1%. All right, so our null hypothesis would be that this group has the same brand loyalty as the general population. Our alternative would be that they are more likely. You know, does this indicate that the population of consumers loyal is more than this 0.47? So again, this is a one-tailed test. All right, so how did I get this information? Well, I'm going to go here and I'm going to say the probability that for a failure rate, remember we're saying alpha is 1%. So that means 1% up here, or you could say 0.99 down there. What's the probability to get that? And you could look on your table and try to find 0.99. And I'm going to cheat because I know it's 2.33. So I got 0.9901. You do that. Or an alternative way is, you remember this little part, where are we at down here? Over here. There we go. This little thing, this interval thing. Well, if you have 1% on this end, that means it corresponds to 1% on that end, which means it would correspond between those two of being 98%. And if I look at that, for the level of level of confidence, it would be 0.98. That's 2.33 as well. So that's another way you can kind of work it out. But you could just look there and say, hey, where on the table is this? That's going to tell me this Z value. So what's going to happen here? If I get a Z value that's 2.33 or more, I'm going to reject this null hypothesis. And I'm going to say, oh yeah, this group is more loyal than that. If I get a value less than 2.33 somewhere over here, I'm going to say, no, I don't. It doesn't appear that they are more loyal. And again, I said equal here. You could say less than or equal to. You know, for all I know, these people could be less loyal to Chevrolet. than other ones. So, the big thing is that the null hypothesis has an equal sign, and this is the one you're testing for. All right, so let's calculate our population proportion, or sorry, our sample proportion. So 490 said they would buy another one out of the 106. That gives us 0.487. All right. Where's my problem? Here we go. So yeah, so we're predicting a population of 0.47. So this is more. So let's calculate our Z value, 1.08. And so how does that compare to our predicted or our cutoff? So going back here, our cutoff was 2.33, right? Our cutoff was 2.33. We got 1.08. Don't reject the null hypothesis. We didn't get far enough away from the mean for that. Enough, sorry, I shouldn't say mean, the predicted proportion. We didn't get far enough away from the predicted proportion to make that claim that this group is more devoted to their brand loyalty than normal. Okay, so there you go. Very similar to what we did in the last couple sections. This is the end of chapter 8. So good luck. Oh, never mind. We're not done. Wait, here we are. I was looking at the wrong one. Where's my little thing here? I think we're done. Yeah, we're done. Okay. Sorry, I was looking at my wrong little handout and thought we weren't done yet, but we are. We're done. So this is chapter 8. We're all done. We're gonna have the test. It's gonna be doing this hypothesis testing. Please be careful. Make sure you set up these hypotheses, and then we're gonna take the test over. Chapter 8. All right, take care. And let me turn this off.